Hello, this is Mrs. Nearing, and this video is about conjugate acid-base pairs and their relative strength and weakness. So we have these things called conjugate acid-base pairs, and the way that you can spot a conjugate acid-base pair is that they only differ by one hydrogen. So for example, you've got HCl as the acid. If you take one hydrogen away, you're left with the chloride ion. That is its conjugate base. HNO3 is an acid. You take a hydrogen away, you're left with NO3. That's the conjugate base. H2CO3, you take one hydrogen away and you're left with HCO3, that's the conjugate base. So they differ by the presence of just one hydrogen. You can go backwards. If you're given a base, you can figure out what the conjugate acid is by just adding a hydrogen. So if we say F- is a conjugate base, you can figure out what its conjugate acid is by adding a hydrogen to it, and that is HF. All right, so we've talked about acid and base strength, and there's this relationship here between these conjugate acid-base pairs, where as the strength of an acid increases, the strength of the conjugate base will decrease. So as the strength of an acid, HA, increases, the strength of its conjugate base, which will be A-, decreases. If the acid is so strong that it is one of our 7 that we call strong acids, then the conjugate base is so weak that it's essentially neutral. So in the example of HCl, the conjugate base of this strong acid, the chloride ion, is so weak that it is neutral. It will not affect the pH of water. If the acid is a weak acid, the conjugate base will be a weak base. And you can have, some weak acids are stronger than others, so you can have relative differences within the weak acid category. Remember, weak acids covers lots of things. It's any acid that isn't part of our 7 acids is a weak acid. So let's look at some examples over here. We've got 3 weak acids from strongest to weakest, and I'm ranking them based on their K values. And remember, K value represents the products over reactants. And if you're thinking about acid dissociation, we are saying the products are the ions. So when we talk about the K value, we're saying how much does it ionize? If it has a large K value, you're making a lot of ions, so it's got relatively high ionization. Strong acids totally ionized, they've got very high K values. Weak acids, typically less than 5% of them ionize, so they've got relatively smaller K values. But there's a wide range within that. So here, if you look at our examples over here, we've got hydrofluoric acid, which is relatively strong for a weak acid. Its K value is 10 to the minus 4th. H2CO3 carbonic acid is 10 to the minus 7th. Hydrocyanic acid is 10 to the negative 10th. So we've got a stronger weak acid and a weaker weak acid. If you look over here at their conjugate bases, since HF is a relatively strong weak acid, the F- ion will be a relatively weak base. Its Kb value is 10 to the negative 11th. If you go down here with HCN, and this is a relatively weak acid, it's got a small K value compared to other weak acids, that means its conjugate base will be stronger. So the cyanide ion is a stronger weak base than the fluoride ion. So these are still all weak, but you can have relative strengths and weaknesses within that category, because again, it's a very big category. So some anions are better at being weak bases than others, and you can tell that based on their K value. So Cn- has a larger K value than F-, meaning when you put this in water, it will make more hydroxide than your fluoride ion will. There's a mathematical relationship here. If you take the Ka value times the Kb value of an acid and its conjugate base, when you multiply them together, you will get Kw, which is 1 times 10 to the negative 14. If you stop and do that with these values, you should find if you multiply this times this, this times this, this times this, you will always get approximately 1 times 10 to the negative 14. So since that's a constant, we can see in this relationship, as my acid strength goes up, I'll have a higher Ka value. That means the strength of the conjugate base will go down because I'll have a lower Kb value. So as one goes up, the other one must go down, and vice versa.